In this video, we're going to find the equation that describes a plane that goes through three given points. And if you're watching this on YouTube, in the bottom right-hand corner under the little cog, if you adjust that setting, you can change the video to be HD, which will help you see the small print. And here is the first picture. So we're just considering these 3 points, P, R, Q in the plane. And we want to find the equation for, sorry, they're not in the plane, they're just in three-dimensional space. And we want to find the equation for the plane that goes through all three. So we learned in elementary school that 3 points determine a plane, and now we're going to see how to get from the points to the plane. Okay, so there's a bunch of sage nonsense going on here. Alright, so to get from the last picture to this next picture, several things have happened. And maybe I can summarize what those things are, then we can go back if we need to and look at the technical stuff. So there are three new vectors here. One is this yellow one that's labeled PQ. So you can see that's the direction from P to Q. And that comes just from subtracting P from Q as a vector. And that happens up here if you care. So here's where PR and PQ get defined. So PR is just vector R minus vector P. PQ is just vector Q minus vector P. So, subtraction gives direction. There's nothing too surprising about that. One thing that is a little weird maybe is that this purple vector, the cross product of PR and PQ, you can see is coming out of the plane determined by PR and PQ at a right angle. Of course, that's what normal vectors, that's what the cross product does, is it gives you a vector orthogonal to the plane spanned by the two original vectors. And you can see that here PQ and PR they're in the plane that we want. That's sort of by coincidence. I picked those points PQ and R kind of lazily so that they happen to be in a plane with the origin. You can imagine that they might be some other place. Doesn't matter. But the important thing is that the plane determined by PR, PQ, and the origin is going to be parallel to the plane determined by P, R, and Q. And so this purple vector, which is normal to the plane determined by PR and PQ, is also going to be normal to the plane determined by PR and Q. Recall that having a normal vector to a plane is a crucial part in finding an equation that describes it. So now that we have all this stuff, how do we get to the equation? So we're getting really close. And so focus your attention, please, on this. So this equation is saying that this is giving sort of the cookbook recipe for describing a plane. Here, n is the normal vector. R is sort of, and think of R as being the x, y, z vector, so it's just a generic point in space that is in the plane, and R0 is some arbitrary but specified point inside the plane. So what makes the normal vector is that it's orthogonal to every vector that is in the plane. And so when you dot product the normal vector with the direction from this point in the plane to this point in the plane, of course it's going to be 0. And then if you just write all this out in symbols, it gives you an equation describing the plane. So that's exactly where this formula comes from. So here R is just x, y, z. N is the normal vector, the purple vector that we found above by taking the cross product of PR and PQ. And R0, what did I use for R0? I forgot. I use vector P. So that's fine because we want the plane that contains P. So I could have picked any one of those original points, P, Q, or R, I just picked P. So P is going to be R0, or generic point in the plane. And so when you do the dot product and the difference, you get this, and that is the equation for the plane. And you can read the normal vector right off here if you want to. So the normal vector that we found is minus 1/2, and the coefficient for y is 0, so it's 0, and 1/2. right? And that's about all there is to it. Oh, I guess now here we can plot that equation, and you can see that it does actually go through the 3 original points. And that's it.